Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
So today is another little clip about forces. And I already used the word weight by passing in my previous clip, so I want to talk a little bit more about this today. So let's say we have a scale. What is a scale? The typical scale is a spring. And you pull this spring with certain force and it becomes longer. And this becomes delta x. Small change in the length of the spring. And so then you calibrate this length, because it turns out that F is proportional to x. F equal chi x. And of course F is a vector, but it's one dimensional, so I write F equal chi x. So kx. So basically you say it doesn't matter if I know this law and I know x, then mean I know F, because this is a linear law and x grows and so much times F grows. X grows twice and force is twice. So I calibrate this distance, millimeters, centimeters, and I say that 1 millimeter is 1 Newton and 2 millimeters is 2 Newton and so on. And this is how the very first scales, spring scales, were introduced, and they were based on the Young formula for the spring, that the spring, as we pull it, becomes longer and elongation is proportional to the force. And of course nowadays when we have those weights and those scales, there's those are electronical. So there is like some kind of platform and there is piezo elements, and those piezo elements, for example, they change the electrical properties like resistance or capacity. I'm not going in all the details. And then there is electrical current flowing, and electrical current flows a little bit more, a little bit less, and based on this we know how much force is applied here, but this ties the electrical property of this material with force that is applied. And this is interesting, but it is way out of the scope of this question, because this scope is based, we put on this scale, and let's put the scale like this. And this is a body, and this is we're holding it, or it's attached to the ceiling, and this becomes longer, and what are the forces? And the forces are as follows. This forces is this, it's gravity, it's mg, and then there is some force that going, I don't know, let's call it P. And this is very similar to the problems that we were looking before in the previous clip. It was mg, excuse me, it was mg and n, and here is mg and p, and mg was equal to n, and this is absolutely the same, mg equal p. Only here we don't see any movement, and here we see a little bit elongation, and this elongation gives us the value of p. But in any case, mg equal p, and this is a way to determine the weight of the body that you're buying on the market or in the grocery store, because P becomes the weight. Here N becomes the weight. So in this situation where the body is stable, it's very important, it's all in balance, there is no acceleration, no movement, everything is fine. And this is how they weigh things in the supermarket. Try to move it. No. She puts it on the scale, and then the reader reads, and you built for such and such pounds of tomato or potatoes that you buy. So, but important thing that this is the weight of the body and it's proportional to the mass, and mg equal p. And that's the whole idea, that the weight equal mg. There is no such physical force as weight. The physical forces here are two. One is gravity and another is the string that pulling it up. Because it's only two bodies that this body is interacting with. One is earth and another is string. So there are two forces, P and mg, and this is real forces. But then they say that m multiplied by g is weight. It's not a force, it's just simply mass multiplied by g. And this is weight. And they also say that it's very important that everything should be very stable. A should be 0. And V should be, well, it doesn't matter about V, but everything is stable. A equal, because, and it's also very important that there are only two forces. Because imagine you in the supermarket and you're buying stuff and you pull it a little bit up. Well, of course, you pull it a little bit up, it's three forces, and the reading on the weight will be less. Or if you push it down, the reading would be more. So it's very important when you measure the mass. In reality, you're measuring mass. You're measuring mass that you're buying. But mass is mass, and mass is in kilograms, and weight is in newtons, and so it's different units. In fact, long time ago there was kilogram, kg mass, and there was kg capital for the force. Those units, but I don't want to go there because it's too complicated. All I wanted to say is that m is mass, and mass multiplied by g is a weight. And weight is not a force. So let me write it down. Weight is not a force. Weight is simply mass multiplied by g. And it so happens that weight is equal gravity, and weight is equal the pull of the string, and weight is equal the normal reaction. And so that's the case, and I will be coming back to this a few times later on, but for the time being it's my first introduction to the weight when I'm talking about forces, but I will be reinforcing this notion a little bit later in following problems when we will be dealing with unweightness, and when we will be dealing with the free falls, and when we will be dealing with body orbital motion around the Earth, and different problems about second law of Newton. But for the time being, once again, all that we have to get used to, the weight is not a real force. Weight is simply multiplication m on g that happens to be equal the gravity force and the tangent force that scales the spring force creates here, or normal reaction if body is on this surface. So I hope this cleared it up a little bit about weights, but I will be returning to this. So if you liked it, like. If you want more, subscribe, bell. If you have problem questions, put it in. Thank you.